Hello everyone, my name is Daniel. I work at Mathspace and this term I'm going to be the Year 9 teacher. So I'm going to be covering some of the concepts in Year 9 and today we're going to be starting with indices. So it's a part of the real numbers and we'll be looking at index laws including the zero power law and negative indices. So welcome, thanks everyone for being here for the very first lesson. What I'm going to do is I'm going to turn on the chat box. I previously turned it off, but I'm going to turn it back on again. And I encourage you all you can speak to one another or you can speak to me as well. If the chat box gets a bit too hectic, if there's a lot of spam or if people are writing things and not being appropriate, I will have to turn off the chat box, okay? But I will turn it on for now and we'll just see how that works, okay? So there's going to be a lot of trial and error today. Okay, so I can see that there's someone it could be an accident, but they keep typing the letter F. So I am actually going to turn off the chat box because that'll be too distracting for everyone, okay? So I'll try it again next week. And if we can get it working, great. But for today, let's just not worry about it. If you've got any questions for me, I encourage you to use the Q&A feature. So when you look in your Zoom, as you move your mouse around, you should see a Q&A, a speech box. And if you click that, that's where you can type a question for me. And again, I ask you to be respectful, please, and to also ask questions that are relevant to what we're talking about today. Okay? Question is all, yes, indices is all that we will be doing today. That's where we're starting. And next week, we'll also move to scientific notation. And so that's what we can look at next week. Okay? So I've answered that question live. Alrighty, I won't answer any more questions for now. This is actually a good one from George. Are all participants muted by default? Yes, they are, because this is a webinar. But what I'll do, I think we've got a lot of people here today. We've got over 25 and we're expecting more. So we might have an opportunity at the end of the class to unmute the microphones, but it would have to be like a one at a time kind of feature in order for people to speak. We do have a schedule for the term. I can see Claire's asked this question. Yes, a scope and sequence. I don't know if it's on the website as of yet. I know it went out in an email, I believe yesterday or the day before. It's a Dropbox document that you can look at and you can look at the scope and sequence. And question from Robin, this is Australian curriculum, not specifically Victorian curriculum. I am a Victorian teacher myself. I'll introduce myself in a moment, but we're going to be covering the Australian curriculum for this term, but we'll hopefully see a lot of parallels. So yeah, okay, I've answered these questions live. And now I will move on to begin. So, welcome, Mathspace Academy, Lesson 1. We're going to be talking today about indices. Before we begin, I should probably introduce myself. So, my name is Daniel O'Kane, and I'm a mathematics educator who works at Mathspace. So, you might have seen my face before if you're someone who uses Mathspace, because in the videos, the worked example videos that appear throughout the textbook, I've created thousands of them over the years. And so often they have my face appearing just in the corner of the screen, much like what you see today in this Zoom webinar. So before I worked at Mathspace, I used to be a mathematics lecturer at Swinburne University. I used to teach engineering maths to students coming into a degree wanting to learn engineering. Now I taught university level maths, but I also taught high school level maths. So I taught some of these students who came from schools where, you know, they didn't have a lot of background in mathematics, but they still wanted to learn engineering. So I teach them, like, I do them a bit of a catch-up course before we jumped into the uni maths. So I've been working for over 10 years as a teacher, both online and in the classroom. So I have experience engaging students online as well. And hopefully that shines through today. So a bit of housekeeping before we begin. These lessons aren't meant to replace what you do in school, okay? I would think of them more as summary lessons. So we can't obviously cover everything that you're doing in school in 1 hour every week, but I want to be able to give you that understanding and hopefully, you know, look at some of these topics that you're learning in school from maybe a different point of view, and also, yeah, just to kind of familiarize yourself, strengthen those concepts that you're learning. I am following along in the Mathspace curriculum, but of course that curriculum is mapped to the Australian curriculum. Now, you don't have to be a Mathspace user to participate and watch these webinars, these classes. You're welcome to not use Mathspace, but if you would like to use Mathspace and you're a student, that's something you can ask your teacher about, okay? These classes are recorded, so if you need to shoot off in the middle of the lesson, that's okay. Or if you ever can't make one of the weekly lessons, you can watch the recordings at a later stage. You just have to wait 24 hours. That's how long it takes for us to get the recordings up online on the website. I'll be using some polls today, so that's my way of engaging you all, and I hope that you will respond to the polls. I'm going to ask some questions. And I have written before that you can use the chat, but I was just having some issues with it before, so let's not worry about that today. So yes, the Q&A is where I'd like you to ask questions. So we've talked about some questions already, but I'll look at that again later in the lesson, the Q&A feature. And I will leave some time at the end of this lesson today to go through as many of those questions as I can. Okay, so we're starting with the first chapter in the Mathspace curriculum, which is the real numbers. And so I've already mentioned this, the real numbers, we're talking about indices. So today we're going to be talking about the index laws. So this could be a lot of revision for you. You might have already seen this in your class, but we're going to specifically talk about the zero power law as well as negative indices. And then next week, we'll take this knowledge of indices and start working with scientific notation. Now, I just wanted to share this with you as well before we start. There's this fantastic maths teacher. His name is Eddie Wu, and he's won a lot of awards nationally in Australia as a maths teacher. And so a lot of his videos are available on our website. So if you go to WooTube, his name's Eddie Wu, so wootube.mathspace.co, you'll actually be able to watch all of his videos. So you can see, I can count, there are 14 videos just around indices and scientific notation. So if you're looking for some more in-depth knowledge, you want to actually learn more about what I'm talking about today in more depth, I highly encourage you to go away and watch these videos. And so he's got videos for everything between, year 7 and year 12. So you can go to that website and check it out. So what are indices? Okay, so just as a quick recap. So when we look at a number 2 to the power of 3, the number 2 is what we call the base. So that is that number that keeps being multiplied. And then the index, another word for index is exponent, and another word for exponent is power. So all of these words are interchangeable. So depending on where you're looking online for any of your resources, you might see this index referred to as other words like exponent or power. So exponent tends to be an American phrase, and power is more of a general term. So 2 to the power of 3 is how I can read this, or 2 with index 3. And so what that means is that base, we see it appearing in a factor tree. So that means it keeps being multiplied by itself 3 times. So the common mistake when students first start learning this is they think 2 to the power of 3 is 6, because all they're doing is 2 times 3, but it's not 2 times 3. 2 to the power of 3 is that base 2, and then how many times is it being multiplied? So in this case, I can see 2 times 2 times 2, which is 2 to the power of 3. And so that's going to be 8. So today I'm going to go through these laws to do with indices. And so the first law that's generally taught is what's called the multiplication law. So I might present this because there's an animation to it. So it's that when you have the same base being multiplied with these powers, so they can be the same powers or they can be different powers, what happens is you're adding the powers. So if I look at 2 to the power of 3 times 2 to the power of 2, for example. 2 to the power of 3, I saw before, was 2 times 2 times 2. And then 2 to the power of 2 is 2 times 2. So when I remove the brackets, because remember, it doesn't matter what order I multiply. If multiplication is the only order that's occurring, it's actually this 2 being multiplied by itself, and that 2 appears 5 times. So then, of course, I can express that as 2 to the power of 5. Well, guess what? 5 I know is 3 plus 2. So this is a little proof to show you that the multiplication law works. I probably shouldn't use the word proof because it's only a proof, it's only an example, okay? It's not, a proof is something that requires a lot more heavy algebra, okay? But that's an example of how the multiplication law works. The next law is the division law, okay? So this is kind of the opposite, right? So if you have a base with 1 power and you divide by the same base, but with a different power, what you're doing is you're finding the difference between those 2 powers. So because we're in year 9, at this point, we're starting to move away from the division symbol and we start focusing more on the fraction symbol. So you're probably going to start to see more and more this dividing in the second way with fractions and less now with the division symbol. So here's an example of why this works. So x to the power of 5, I know is x times x times x times x times x. So that x appears 5 times. And then when I divide by x cubed, I see x times x times x. So that x is being multiplied. I see that base appearing 3 times. So what happens, oops, I'm missing one of those red lines. So 3 x's from the numerator and the denominator can divide out. So then you're left with just the 2 x's in the denominator. So they cancel out. So then that just leaves you with x squared. Well, guess what? X squared, that is x to the power of 5 minus 3. So you don't have to do all this work when you start to use index laws to simplify. Once you understand the laws, you can just go straight from that first step to the last step. You can just immediately find the difference between those powers and then find that answer to be x squared. The next law I want to talk about is the power of a power law. So when you have a base raised to a given power, and then you wrap that in brackets and then you raise this whole number to another power, it's the same as just multiplying those powers together. So here's an example, 3 squared to the power of 4. I know if I just consider 3 squared to be a number, so let's say that was 2 to the power of 4, I know it would be 2 times 2 times 2 times 2. Well, 3 squared being raised to the power of 4, that's going to be 3 squared times 3 squared times 3 squared times 3 squared. I see 3 squared appearing 4 times. Well, using that first index law, the multiplication law, I know because it's that same base appearing each time, I can just add those powers together. So 2 plus 2 plus 2 plus 2, that's 3 to the power of 8. Well, 8 is of course 2 times 4. I see those 4 groups of 2 being added together. So that's how this law works. You're multiplying those powers together. I actually forgot to do one of my polls before, so I might just take a quick moment to actually go through this. I should have done this at the very start. So I'm going to share a poll. I'd like to know, for everyone who's here today, have you done any work on indices this year at school? So maybe you have, maybe this was something you did in term 1, or perhaps you haven't done it in school yet and you are in year 9, and maybe it's something that you're going to cover in class later. So I would love everyone now. No one seems to be answering the poll at the moment. Sometimes there can be an issue with these polls. So I'm just going to stop the poll and I'm going to share it again. I'm going to relaunch the poll and hopefully now you'll see it on your screen and it's something that you can answer. Okay, so I want to know, have you done indices yet at school this year. If you're a Year 9 teacher, sorry, a Year 9 student. If you're a Year 9 teacher, you're more than welcome to answer this as well. So we've got 12 out of the 25 participants today have voted so far. So I'll just give everyone a couple more moments to vote. Okay, so just trying to get a gauge of where we're at. Hopefully, even if you haven't done it this year, you are still following along. And I wouldn't stress if there's no full, complete understanding once you leave today, if you haven't done indices, because you'll probably find that when you do cover this with your teacher later in the year, you'll pick it up very quickly. Okay, I'm going to stop the poll. Thank you very much. And I'm going to share the results with everyone now. So I can see that 61% of the people here today have covered indices today, which is great, fantastic. Hopefully today you will then now get more understanding of what you covered if you've done this in term 1 already. Okay. All right. Let's move on. Actually, I've got a question that we can now go through. So I'm just going to change tabs. Please give me a moment. So once you start learning these laws, you then can start to mix and match. You can start to use several laws at the same time in order to be able to simplify a question. So here's a question that I've just opened up in Mathspace that I'm going to work through with everyone. So simplifying this expression, 17 to the power of 9 to the power of 3 times 17 to the power of 6 divided by 17 to the power of 24. Now, if you didn't know index laws, you had to write the 17 out over and over and over again in the numerator and denominator and then cancel out, this would take a really long time. But with the index laws, this is going to be much faster. So, starting with 17 to, 17, not 19, starting with 17 to the power of 9 to the power of 3, remember we had that power of a power law, so that this can be evaluated to be 17 to the power of 9 times 3. And so that's going to be 17 to the power of 27. So, my first step, I could write in the numerator 17 to the power of 27 and then multiply this by 17 to the power of 6. And then I'm dividing this whole result by 17 to the power of 24. So that's my first step that I would do as I do this one at a time. So I've used that third law, the power of a power law. Now I'm going to use the first law, the multiplication law, to simplify what's in the numerator. So I can look at now what's in the numerator, which is 17 to the power of 27 times 17 to the power of 6. So remember, I see that same base, 17, so I know I can add the powers. So 17 to the power of 27 plus 6 using that first index law. So this is going to be 17 to the power of 33. So now I can write that in my numerator. I can write 17 to the power of 33. And I'm dividing this by 17 to the power of 24. The final step now is to use the division law, that second law that I covered today. So, because I've got 17 to the power of 33 divided by 17 to the power of 24. So I see that same base appearing in the numerator and the denominator, which means I can just find the difference between these powers. So I can do 17 to the power of 33 minus 24. So I'm welcome to include that in my work in Mathspace, 17 to the power of 33 minus 24. And so that's going to be now 17 to the power of 9. So I'm not required in this particular question to work out what 17 to the power of 9 is. I was asked to give the answer in index form. So giving an answer in index form means I'm writing that base and power as my final answer. So Once you start learning these index laws, it's easy enough to work on questions where it's just one index law and that's it. The challenge is starting to use multiple index laws at the same time for the one question. Okay, let's jump back to the slides now. So the next power law is the zero power law. So any base to the power of 0 is equal to 1. Okay? So if I look at a proof, or just an example of why this works, think of 100 divided by 100. You know that any number divided by itself is always equal to 1. Now I can write 100 as 10 squared. So 10 squared divided by 10 squared is 1. And I know that's true because it's the same number appearing in both what's being divided. Now, using our index laws, specifically the division law, that second law that we covered today, I know 10 squared divided by 10 squared can also be expressed as 10 to the power of 2 minus 2. And 2 minus 2, I know, is 0. So if 10 squared divided by 10 squared is 1, and 10 squared divided by 10 squared is also 10 to the power of 0, that means, therefore, 10 to the power of 0 is equal to 1. So you can do this with any number. It doesn't have to be 10. It can be 2. It could be -2, as long as you've got the brackets around the -2 and then you raise to the power. It can be any number you like to demonstrate this. Before we continue, I am going to ask you my next poll question. So, what about 0 to the power of 0? What do you think that would equal? So this is a really interesting case, okay? So I've got some options here that you can choose. I can see some people are answering, so I know the poll's working, great. So what about 0 to the power of 0? What do you think that would be? So I'll give people a few moments to, just take a guess. If you don't know, just what do you think it would be? See, any base to the power of 0 is always equal to 1, but what about for 0? Would 0 to the power of 0 be 1, according to this law? I'll give everyone just 10 more seconds to answer. Please take a guess. Fire away. Okay, thank you very much. I'll share the results with you all in a moment. But what I might do first is I might share my whiteboard and just work through this with you on the whiteboard first. So, yes, it's true that a to the power of 0 is equal to 1, okay? But if you look at a number like 2, for example, 2 to the power of 0, that is equal to 1, right? And that's how this index law works. But when I look at 0 to the power of 1, I know that's equal to 0. Or 0 to the power of 2, that would be 0 times 0. Which is 0. But 0 to the power of 0 is an interesting case. So if I do that, the example similar to what I did with the 10 squared, okay? So if I did 0 to the power of 0, it's the same as 0 squared divided by 0 squared, right? Because that would be 0 to the power of 2 minus 2. Which is just 0 to the power of 0. But 0 squared is 0, and then 0 squared is 0. The issue is you can never divide by 0. Okay, if you try in your calculator, if you write any number, it doesn't have to be 0, try 1 and you divide by 0, or 5 and divide by 0, you get an undefined number. It's not possible to define that answer. Okay, and it's the same with 0 over 0. So the correct answer, according to that poll, Let me just share the results. So I'm sharing the results with everyone now. So some people did guess 0, some people did guess 1. No one said none of the above. I thought I might trick some people with that, but no one answered that. The correct answer, which I can see 8 people did get correct, which was it cannot be defined. So you cannot divide a number by 0. So 0 to the power of 0 does not exist. It's not something that can be defined. So if I just go back to my whiteboard for a moment. So there is an exception to the power rule. So a to the power of 0 does equal 1 for every number except 0. So if you ever see the rule written like this and you have this little addition at the bottom, okay, that's the reason why. Because if there's a base 0, you can't raise it to the power of 0. It's not something that you can define, okay? All right. I'm going to share my screen again. We'll go back to the slides. And we will continue. So now we're going to talk about the negative index law. So when you take a base and you raise it to a negative number, the law is that it's the same as finding the reciprocal of that base with a positive power. So if I look at an example, 2 to the power of -1, that is the same as 1 divided by 2 to the power of 1. So then that would be 1/2, because any number to the power of 1 is just that number, okay? 2 to the power of 1 is 2, 5 to the power of 1 is 5, 100 to the power of 1 is 100. That base doesn't change because it's just the number appearing once. If I look at something like y to the power of -3, okay, that will equal 1 over y to the power of +3. So that's how you use this law. What I'm going to do now is I'm going to Alt-Tab. So this is a little applet. It's from a website called GeoGebra, geogebra.org. So this is open source teaching and learning resources. So if you're ever having a hard time understanding a concept, or if you're a teacher and you want a tool to help teach your students, geogebra.org is a great place to come. And so I just searched for indices and I got this little widget. So if I look at 3 to the power of 1, I know that's 3. And then when I multiply that by 3, I get 3 squared. I multiply that by 3, I get 3 cubed. I multiply it by 3 again, I get 3 to the power of 4. So this is that multiplication law in action now. So that every time you're adding 1 to the power of a base, you are multiplying by that base. And it's the same in reverse. So when you minus 1 off the power, you are dividing by 3. Minus another 1 off the power. So 3 squared divided by 3 would just become 3. Now with the 0 power law, we have seen that 3 to the power of 0 is equal to 1. Okay, and you can read that as 3 to the power of 1 divided by 3 to the power of 1 makes 3 to the power of 0 by the division law. And also 3 divided by 3 is 1. We've explained that already with the 0 power law. What we're doing when we now divide by 3 again, you would subtract 1 off the power. So 3 to the power of -1, it's the same as 1 over 3 to the power of 1. But just think of it as every time you subtract 1 off the power, you're dividing by that base. So take another 1 off the power and you divide by 3 again. So you're going to have the 3 appearing twice in the denominator. So that's 3 squared. Take another 1 off the power, you get 3 to the power of -3. Okay, and then you're dividing that 1 by 3 times. So that's 3 cubed. So you can do the same with a letter. Okay, it doesn't have to be just with numbers. So if I look at c to the power of 1, that's c squared, c times c. So every time we add 1 to the power, we multiply again by that base of c. So now when we start to divide by c or c squared or c cubed or c to the power of 4, okay? We're dividing each time by c cubed, c times c, or c to the power of 4, c times c times c times c, okay? So hopefully that's, if you were struggling with negative indices before, because it is a difficult concept when you first learn it, hopefully now it's starting to make some more sense, okay? Now, I'm going to go through another example in Mathspace, okay? So 5 to the power of -8 times 5 to the power of -4 divided by 5 to the power of -10. So this is a similar example before, that now we're using multiple index laws at once to simplify an expression, okay? But now we have to include this possibility of negative indices. That previous example I didn't involve any negative indices, but now we're going to have to work with that, okay? So there are different ways that you can tackle this problem, okay? I'll do one way first, and then I'll do it again using another way, okay? So similar to before, I'm going to start with looking at the numerator of the whole fraction of this expression. So that's 5 to the power of -8 times 5 to the power of -4. This will equal 5 to the power of, according to that multiplication law, you add the powers, but you have to be really careful with the negatives, because I'm taking -8, that first power, and then I'm adding -4. So when you first start learning this, you first start working with negative indices, I recommend using these brackets and just doing this one at a time so that you don't lose track. Because if you read this very quickly, you might just think you add 4 to -8 and then get an answer of -4. But that's not true, because I'm adding a negative number. Remember, that is the same as subtracting that number. So this is going to be 5 to the power of -8 minus 4, which is 5 to the power of -12. Okay, so now in my first step, I can write 5 to the power of, now in Mathspace, you do have the ability to show your work. So you could write that first step out just like I did on the sketchpad, but then just remember that I'm dividing that result by 5 to the power of -10. You can do that, but I've already done this work on the sketchpad, so I can write this as 5 to the power of -12. And now I'm dividing this by 5 to the power of -10, okay? So really, when you think about it, I'm not actually using that index law, which was a to the power of -m equals 1 over a to the power of m. I'm not actually using this law yet. I'm just using the other laws, the multiplication law and the division law. It might be something that I use for the end, okay? So now looking at 5 to the power of -12 divided by 5 to the power of -10, I'm going to use the division law, which we did at the start of the class, okay? So I know this is going to become, I've got that same base appearing in the numerator and denominator, okay? So it is a good idea to double check that, because if that was a 5 and then the bottom number was a 6, you couldn't do anything with the powers, right? But because these bases are the same, I can use that division law. So I can now find the difference between these numbers. But what I'm going to have to do now is, again, be careful of those negatives, because it's going to be 5 to the power of -12, and I am subtracting -10, okay? So we're going very slow here so that we don't make mistakes with the negatives. So if I'm subtracting -10, that's going to be the same as adding the 10. So -12 plus 10, I get 5 to the power of -2. Okay, so you can show that work in Mathspace if you're using Mathspace. However, I'm just going to write this in straight away. 5 to the power of -2. Now, if my question said, write this answer using a negative index, Job done. I'd be finished. I wouldn't have to do any more. But let's just carefully read the instruction. We have to use index laws and then evaluate. So because this isn't an X, it's a 5, okay, I can actually evaluate. I can find the answer. So now we need to use, I'll write it again on the screen, that negative index law. Base to the power of m. Negative m, I should say, is 1 over that base to the power with the positive power. Okay, so 5 to the power of negative 2, I can write that now as 1 over 5 to the power of positive 2. So 1 is being divided by 5 twice. That's how you can read that expression. 5 squared, 25. So then this whole expression has finally evaluated to become 1 over 25. So we used the multiplication law, we used the division law, and we used this new negative index law to solve this problem. Now, very quickly, there are other ways to answer this question. I mean, I like that particular method, but I mean, if we start again, we go 5 to the power of negative 8 times 5 to the power of negative 4 divided by 5 to the power of negative 10. You could have expressed all of these 3 bases with the negative powers. Could have used that index, that negative index law straight away. So it creates a lot of fractions within fractions, but as long as you keep track of it, this is a perfectly legitimate way of answering this question. So then when it comes to multiplying fractions, remember you multiply the numerators and you multiply the denominators. Okay. So then this is going to become 1 times 1, which is 1, divided by 5 to the power of 8 times 5 to the power of 4. And then all of this gets divided by 1 to the power of, 1 divided by 5 to the power of positive 10. Okay. Now, when you're working with fractions within fractions, I do recommend bringing back the division symbol. It makes these algebraic or these fractions within fractions easier to read. Okay. So this is the same as 1 over 5 to the power of 8 times 5 to the power of 4. And then you're dividing this by 1 over 5 to the power of 10. Okay. So now we can use the multiplication law to simplify this. Okay, it becomes 1 over 5 to the power of 12. And then remember, when you're dividing a fraction, it's the same as changing this to a multiplication and taking the reciprocal of that second fraction. So then that becomes 5 to the power of 10 over 1. So now these, again, I multiply fractions, multiply the numerators, multiply the denominators, and I will get 5 to the power of 10 divided by 5 to the power of 12. So then I can use that division law to do 5 to the power of 10 minus 12, which is 5 to the power of negative 2. And then I use the negative index law again to find that answer to be 1 over 5 squared, which was 1 over 25. So there are different ways you can use the index laws in different orders sometimes, as long as you're following correct order of operations. Okay. Great. All right, I'm going to go back to my slides now because I have another poll question that I want to ask you. It's the last one of the day. Okay. I'm going to stop sharing these results. I'm doing my next poll. Okay, so for the final poll for today, I'll launch the poll now. The question is, for numbers with a negative index, what can that base be? So remember when we looked at the 0 power law, there was an exception, okay? There was a number that didn't work, but for every other number, it was good, okay? I am asking a similar question in a different way. So that's a clue for you, all right? I'm not getting any answers to the poll so far, so we might be having another Zoom issue. I might just stop the poll and start it again. Okay, we'll see if you can see that now. So for numbers with a negative index, can we only work with positive numbers? Can we work with positive and negative whole numbers? Can we work with all integers? Or is it anything except 0? Okay, so maybe I'll share my whiteboard just to give you an idea of what I'm talking about. So my question is, okay, when I'm using this law, a to the power of a negative base equals 1 over a to the m, I'm looking at all the possible numbers I can substitute for this letter a, okay? So you might think it is answer A, okay? Positive numbers only, all right? So maybe we can only do 2 to the power of negative 2, or 5 to the power of negative 3, because that's all the examples I've shown you so far. But maybe it includes negative numbers as well. So negative squared to the power of negative 2. Does that work? I say it does work, right? I'm giving you a clue here. So that would just be 1 over negative 2 to the power of positive 2, and that just becomes 1 over 4. So negative numbers work and positive numbers work. Now, be careful of the word whole numbers, okay? So maybe this doesn't work for just whole numbers. Maybe it works for decimals too, okay? So what if I did 0.2 to the power of negative 1? Well, that would just be 1 over 0.2 to the power of positive 1, which is 1 over 0.2, okay? It's the same as 1 divided by 1/5, because 1/5 is 0.2. But I'm evaluating this on the board, okay? So all integers, these are all numbers that are whole numbers, okay? But actually this works for fractions, this works for decimals, this works for positive fractions or negative decimals, okay? There is only, again, one number where this is not going to work. And so I can see that 3 out of the 5 people who voted in this poll got that correct. It is any number except 0. Oh, we just updated at the end there, and a few more people answer. So I'll share the results. So actually, you can do this for any number except 0. So if you look at 0 to the power of negative 3, for example, well, using the index law, that would become 1 over 0 to the power of positive 3. And that would then be 1 over 0. So then we get that same problem as before. We're dividing by 0 and you can't divide by 0. So when you see that law, a to the power of negative m equals 1 over a to the power of positive m, again, there is that exception. The base can never equal 0. So it can't equal 0, but it can equal everything else. It can be fractions, it can be rational numbers, it can be irrational numbers, it can be all the numbers except 0. Okay, we're getting close to the end, I think. Let me just share the slides again. There was this proof of negative indices that I did create, which I can go through with you. So it was similar to what we did on that GeoGebra widget. So y squared divided by y cubed equals y to the power of 2 minus 3, which equals y to the power of negative 1. Okay, and that is the same as 1 over y. Okay, and I know that to be true because Another way I can evaluate y squared over y cubed is I can have y times y in the numerator. I can see that y appearing twice. And then y times y in the denominator, y cubed. And then what happens is the two y's cancel in the numerator and the denominator, so you're just left with 1 over y. So that is how y to the power of -1 equals 1 over y. Okay, so that is just a recap of the first 2 lessons in the Mathspace curriculum for real numbers. So that is for the index laws, revision, and then also looking at those non-positive indices. So that's powers of 0 and also negative indices. Okay, so for anyone with Mathspace, what you can now do as a student is you can log into your dashboard, you can go to your topics, you can go to the Australian or whatever state you're in, it'll probably be similar, okay? You go find the work with indices, and then you can complete now on your own 2 tasks. You can complete the task on index laws, and you can complete the task on non-positive indices, okay? I'm going to answer some questions first, and then if there are anyone in the webinar that is using Mathspace at home or at school, I can take you through how to find those topics so that you can then go away and work on some questions of what we've done today. Okay. So now I'm going to open up the Q&A. Okay, so someone mentioned that they couldn't see the poll. Okay, sometimes this does happen for users in Zoom. So if you are using Zoom today in a browser and you didn't download the app, that's fine. It's just that you then can't see the polls. So whenever you log into a Zoom webinar and it asks you to open the program in the Zoom app, or maybe it might ask you to download the Zoom app, if you want to be able to see polls in these classes, you do need to download that app and then to watch this webinar in that app. That's often an issue that I have had with other people when they can't see the poll working. So I do recommend doing it like that, and that way you can see the polls and participate. Not the end of the world if you can't see the poll. I mean, you can still listen along and watch, but it is good to be able to see the polls when you're in webinars like this one in Zoom. I've had someone else ask, are you able to use or trial the shared whiteboard? Those that have a tablet may be able to participate or contribute to the next worked example. That's a fantastic idea, George. I think in Zoom webinars, I'm not sure if you're able to share the whiteboard. I know in Zoom meetings you are. So if you're a student or a teacher and you're using Zoom at your school and you set up a Zoom meeting, I know you can definitely share the whiteboard. Everyone can just get on there and write it. So then I can, pass control over to different students. But I believe in a webinar, it's more difficult because it's more that I'm the presenter and everyone is an attendee and they don't have those rights. I'll just have a quick look at the options to see if there is a way to kind of hand over control to a particular student by choice. I can't see that at the moment, so it might be something that I have to play with, and then we can try to do that next class. Another question from Desi. I'm a teacher. Did you create the PowerPoints for this presentation? Are the features you used for Zoom only? Great question. So I did create a PowerPoint for the slides. I did that in Google Slides. So I just, with my Google account, I created a slideshow that I was just, that I animated myself. And I used an add-on called Maths Equations to be able to generate those images of math equations. The features that I'm using today, they're usually common in other platforms like Google Hangouts, also MS Teams. That ability to share the screen is really what's important, so that then you can share what's on your screen and then all the students in your class can then see what's on your screen as you're presenting. And I definitely know all those platforms do that. And also, if you're in a meeting and not a webinar, talking specifically about Zoom now, the students themselves can also share their screens so that that way everyone can show each other work. The polls are built into Zoom for anyone who is curious of how I created those polls. So when you run a Zoom meeting or a Zoom webinar, if you're the one who's running it, you have the ability to build in the polls beforehand. Again, if it's a meeting and not a webinar, you can actually create the polls on the fly. You can just straight away put them in. But because I'm running a webinar where I'm presenting to multiple people today, that's why I had to build in the polls beforehand. Next question. Yeah. So thanks very much everyone for coming. I'm happy to stick around for another 5 minutes, especially if there are any students that would like any help with a particular question that they might be working on when it comes to indices. I'm happy for you to write in the Q&A. I might even turn on the chat again, see how that's working. So if you would like to write to me in the chat box, or if you would like to write a question, I'm happy to help you if you've got a question about indices. If there's something that you're still having trouble with, having trouble understanding, I would be more than happy to help. I suspect we might have a lot of teachers here today. I know I invited some teachers to come along, and it's the school holidays. So this isn't, this is going to be something we're going to be running every week. So even if you're watching the recording of this at home, that's perfectly fine. What you can do is you can enroll and then attend live next week. Okay, it's not something that you've missed the boat if you didn't enroll today or whatever. Like, it's something that you'll be able to enroll in later if you wish. Something in the chat box. Do I know Dr. Andre Podolsky from Swinburne? No, I don't, George. Unfortunately, it's been about 5 years since I worked at Swinburne, and that was in the TAFE department. So if there was anyone in the university department, I didn't really have much access to them. I worked with a few individuals in the TAFE engineering department. And so that's why I was supporting students as they kind of took a pathways program to their degree, and it did include some first year uni units. Great. Yeah, look, we are pretty much finishing now. So if you've got to get going, or, you're in Victoria and you want to enjoy the lovely sun outside, safely, only for exercising and not for any other purposes. I shouldn't be encouraging everyone to go outside. Apologies. And yes, for anyone who's not in Victoria, if you're in another part of the country, you're in school at the moment perhaps, and maybe you're watching this as a part of your schoolwork. Thank you for coming. And we will be running another session next week. So we're going to continue this term 1 revision. So, a lot of schools tend to teach this content at the beginning of the year. So I'm going to continue with the indices and do scientific notation next week. And so we'll look at some practical examples of scientific notation as well. It won't just be learning the theory. We'll look at, how scientists use scientific notation, how engineers use scientific notation for their work. So I do encourage you to keep coming along and to keep up with the learning. I will stick around for a couple more minutes. So if there are any more questions, please feel free to fire away, especially if you are a student who would like me to maybe go over a worked example. I'm happy to do that if there's a particular index law. There were some variations of the index laws that I didn't go through today, and you might know this, especially if you're a teacher. So what I might do is just share the whiteboard. There were some variations that I do like to teach. So a fraction, when you raise a fraction to a given power, there is a rule that says that it's just raising the numerator and the denominator by the same power. It's the same when you look at the product of two numbers. and you raise it to a power, it's the same as raising each of those terms in the product by the same power. So we can look at derivations of that. So I'll start with that second law, A times B. Let's just look at cubed, for example. I know that's just A times B times A times B times A times B. And any students left in the webinar, I do want you to note that when you get to year 9 and you start working in year 10 and year 11, you start to move away from that multiplication symbol X and you start working more with a dot. So a dot in algebra, when it's not at the bottom to represent a decimal, when it's kind of up at the center, that represents multiplication. So you'll remember that I said earlier in the webinar today, it doesn't matter what order you multiply. So if multiplication is the only operation you're working with, you can strip away those brackets and then just change the order. So I can multiply all those A's together and then all those B's together. So that's how I get A cubed and B cubed. So as you can see, that power has gone to both terms in the product in those brackets. And so you can do a very similar derivation with A over B. So, I mean, why not? I've still got 2 minutes. I'll do it on the board. So looking at A over B, and I'll just do this with a square term, okay? It's the same as A over B times A over B. And so when we multiply fractions, remember it's multiplying those numerators together and dividing by the product of those denominators. So then A times A is A squared, B times B is B squared. So again, I can see that power went to both the numerator and the denominator. Okay, I'm going to look at the questions one last time, getting a few thank yous. Absolute pleasure. Thank you all for coming. I believe that is it. So I can dismiss that question. Yeah, these are all just thank yous. Okay, great. Thanks very much for coming, everyone. I'm going to wrap up there and I'll see you all next week. Okay, so next week we're going to be scientific notation. All right. Thanks very much for coming, and especially if you're a student, thank you teachers as well for coming along. Hopefully this has given you some ideas for as you go into next week's teaching. But for the students, please stick with the maths. I know this is a challenging time that we're working in, and I know we're not used to doing all of our schoolwork online, and do give your teachers some patience, okay? Because it is something that they're doing for the first time as well. And, you know, just like I stumbled a few times today, your teachers might as well. So we will get through this, you know, and hopefully it's just for term 2, but it might be for term 3 as well. So we will see, okay? Thanks very much for coming. And for those of you watching the recording, thanks very much for sticking through to the end. My name's Daniel O'Kane. I'm your Year 9 maths teacher at Mathspace Academy. I'll see you next week. Thanks very much. Bye.